Hey guys, welcome back. In this episode of Mind a Snap, we're diving into one of the most mind-blowing cosmic discoveries that most people have never even heard about. And honestly, when you understand the scale of what we're talking about, it's going to completely change how you see the universe. Scientists just released something that sounds like science fiction, but it's 100% real. We're talking about a map so detailed, so enormous, that it makes every cosmic image you've ever seen look like a tiny thumbnail. And here's the wild part. You can actually explore it yourself right now for free on your computer. This isn't just another space discovery that looks pretty on a poster. This data set is actively reshaping how astronomers understand the cosmos, from the structure of galaxies to the ultimate fate of the universe itself. And in the next 25 minutes, we're going to walk through exactly what it is, why it matters, and what it reveals about our place in this incomprehensibly vast cosmos. So stick around, because by the end of this, you're going to see the universe in a completely different way. Hey, so imagine this. Scientists just created a photograph of the universe is so detailed that it contains 5.6 trillion pixels. That's not a typo. 5.6 trillion. Let that number sink in for a second. To put that in perspective, if you printed this image at normal resolution, it would be roughly the size of 3,000 football fields. Imagine a photograph so massive that you couldn't fit it in a stadium. You'd need to spread it across an entire city. That's how big we're talking. But here's the thing that makes this even more mind-blowing. That massive image doesn't just contain random noise or empty space. Inside those 5.6 trillion pixels, astronomers have cataloged nearly 4 billion individual celestial objects. 4 billion. That's not just 4 billion tiny dots either. Each one of these is a star, a galaxy, a quasar, or some other cosmic phenomenon. Each one is a distinct object that scientists have now mapped and cataloged. This isn't some science fiction concept that we're theorizing about. This is real. It was just released to the public recently, and it's fundamentally changing how astronomers understand the entire cosmos. The map is called the DESI Legacy Imaging Surveys dataset. It covers about 75% of the entire visible sky. It took 13 years of continuous observations and 263,000 individual telescope exposures to create. If you tried to do this by hand, photographing each galaxy one at a time, you'd need thousands of lifetimes to complete this project. And here's the best part. It's completely free. Anyone with an internet connection can access it right now. You don't need expensive equipment. You don't need a PhD. You can literally zoom through 4 billion objects scattered across the universe, zooming from the closest stars to distant galaxies billions of light years away. It's like Google Earth, but for the entire cosmos. This is the story of humanity's largest attempt to map our cosmic neighborhood. And what we discovered in the process is going to absolutely change how we see the universe. Now, to understand why this 5.6 trillion pixel dataset is such a big deal, we need to step back and talk about a problem that astronomers have been wrestling with for literally centuries. For thousands of years, humans looked up at the night sky and assumed that what we saw was basically everything. The stars were these distant lights arranged in constellations. That was the universe. That was it. But then telescopes came along and completely changed the game. By the 1900s, astronomers realized something shocking. The Milky Way wasn't the only galaxy. There were other galaxies out there, billions of them, each one containing billions of stars. Suddenly, the universe wasn't just bigger, It was almost incomprehensibly larger than anyone had previously imagined. But here's where the real challenge started. Once astronomers knew that billions of galaxies existed, they wanted the next logical thing, a complete map. Not just knowing that galaxies exist somewhere out there, but actually knowing where they are. What's their position in space? How far away are they? How are they arranged relative to each other? Sounds simple, right? But the scale is absolutely staggering. The observable universe is so vast that mapping it is like trying to count every grain of sand on Earth, except the grains of sand are galaxies containing trillions of stars each, and they're spread across billions of light years. For most of history, this task seemed impossible. Telescopes could photograph small patches of sky, but to map the entire universe would take thousands of years. You'd need to photograph millions of tiny regions, each one revealing thousands of objects, and somehow stitch them all together into one cohesive picture. For centuries, this was just a dream. But then something incredible happened. Computers got faster, cameras got better, telescopes became more efficient, and suddenly something that once seemed impossible started to look achievable. By the early 2000s, scientists had developed sophisticated new techniques. Robotic telescopes could automatically scan the sky. Massive digital cameras could capture thousands of galaxies in a single exposure. Supercomputers could process the incomprehensible amount of data that these telescopes generated. The pieces were finally in place to actually attempt what had always seemed impossible, a comprehensive map of the observable universe. Scientists realized they needed to coordinate. They needed multiple telescopes working together. They needed standardized methods for processing data. They needed to pool resources and expertise from institutions around the world. And that's when something really cool happened. The DESI Legacy Imaging Surveys project was born. This was going to be the project that finally answered the ancient question, what's out there? All right, so let's dive into the actual details of how scientists built this 5.6 trillion pixel map. Because the scale of this operation is genuinely staggering, and understanding the numbers helps you appreciate just how ambitious this project actually was. Let's start with what a pixel actually is. A pixel is the smallest unit of a digital image. If you zoom into any photograph on your computer screen far enough, you'll eventually see individual pixels, tiny squares of color that combine together to form the complete image. In a typical smartphone photo, maybe 12 megapixels, you have 12 million pixels total. That sounds huge when you're just taking pictures of your friends, right? 12 million individual color squares arranged to make a photo. Now compare that to the DESI Legacy dataset, 5.6 trillion pixels. Let me put that in another way. The cosmic map has roughly 467,000 times more pixels than a standard smartphone photo. If you tried to display this image on a modern 4K television screen, which has about 8 million pixels, you would need over 700,000 4K screens placed right next to each other to view the entire map at its full resolution. You could literally tile 4K televisions across an entire football field, and it still wouldn't be enough. So how did scientists actually create something this massive? The data came from physical photographs taken by real telescopes over a 13-year period. This wasn't computer-generated imagery or AI-created content. This was actual light from space captured by some of the world's most advanced astronomical instruments. They used two main telescopes for this project. the Mayal telescope at Kitt Peak in Arizona, that's a 3.8-meter telescope, and the Blanco telescope at Cerro Tololo in Chile, that's a 4-meter telescope. Now, these aren't the largest telescopes in the world. The very largest telescopes are significantly bigger. But what makes these telescopes special is their field of view combined with their camera technology. The cameras mounted on these telescopes are called wide-field imagers, and they're remarkable pieces of engineering. The dark energy camera, or DE-CAM, mounted on the Blanco telescope has 570 megapixels. That's just one camera with more total pixels than you'd find in 100 modern smartphones combined. But again, it's not just the resolution, it's the field of view. This camera can photograph a patch of sky roughly equivalent to the size of the full moon, as seen from Earth in a single exposure. That's massive coverage. Here's how the process worked. Astronomers would point the telescope at the specific region of the sky. The wide-field camera would take a photograph. That photograph captured thousands or millions of objects. The data was recorded and stored. Then the telescope would move slightly and take another photograph of an adjacent region, then another, then another. This process repeated thousands and thousands of times over 13 years. In total, astronomers collected 263,407 individual telescope exposures. That's not a typo. Over 260,000 separate photographs, each one capturing a different patch of sky, each one containing data about thousands or millions of objects. Now here's something important. Many of these exposures overlap. The same region of sky was photographed multiple times from slightly different angles or under different atmospheric conditions. This redundancy is crucial for data quality. When scientists combine multiple overlapping photographs of the same region, they can use advanced mathematical techniques to cancel out atmospheric distortion, telescope artifacts, and other noise. The result is an incredibly clean, high-quality image of each region. After collecting all 263,407 exposures, the data processing phase began. And this is where things get really intense. Raw telescope data is messy. It contains instrumental artifacts from the telescope itself. It has background noise. Cosmic rays from space occasionally hit the camera and create false signals. All of this garbage data has to be carefully removed and corrected. Scientists developed specialized software to handle this processing. But here's the thing. The amount of data is so enormous that even the best computers were overwhelmed. So they turned to Perlmutter, one of the most powerful supercomputers in the entire world. They loaded all 263,407 exposures into Perlmutter and told it to process everything. And Perlmutter ran continuously without stopping for 8 full weeks. That's 2 months of non-stop computation just to clean up and process the raw data from all those exposures. When Perlmutter finally finished, after 8 weeks of crunching numbers, the result was this massive dataset, 5.6 trillion pixels of cosmic data, the largest 2D astronomical dataset ever assembled by humankind. But wait, there's one more layer of sophistication here. The cameras didn't just photograph visible light. They photographed in multiple different colors or wavelengths simultaneously. Infrared light, red light, green light, blue light, and ultraviolet light. This multi-wavelength approach is genuinely important because different types of objects emit light at different wavelengths. Regular stars emit mostly visible light. If you look at them through a blue filter, you see them. Through an infrared filter, they're less bright. But distant galaxies? They're so far away that the light from them gets redshifted, stretched toward longer wavelengths. as the universe's expansion stretches the light waves. So a galaxy that originally emitted visible light might appear infrared by the time it reaches Earth. By capturing data in multiple wavelengths, the survey reveals objects that would be completely invisible if you only looked in one color. Dust-obscured objects are another example. Some galaxies have thick clouds of dust around them. In visible light, you can't see these galaxies because the dust blocks the light. But infrared light penetrates through dust more easily. So by including infrared data, the survey captures galaxies that would be invisible in a visible light-only survey. The end result of all this is a catalog of 4 billion individual astronomical objects, 4 billion distinct targets, stars, galaxies, quasars, nebulae, and other cosmic phenomena. Each object is cataloged with precise measurements: its position on the sky, its brightness in each color band, estimated properties based on its colors, and preliminary distance estimates. And here's the really cool part: the dataset is publicly available. The Legacy Survey Skyviewer website lets anyone anywhere in the world zoom through this cosmic dataset. You don't need the special software. You don't need to be a professional astronomer. You just go to the website and you can start exploring. You can zoom from a wide view showing billions of galaxies to a tight focus on individual stars. You can see the structure of galaxies, the organization of galaxy clusters, and the vast empty voids between structures. It's like having a time machine that shows you not just individual objects, but the entire architecture of the cosmos. So with 4 billion objects now cataloged, what did astronomers actually find when they started analyzing this massive data set? What does the universe look like when you can see nearly every galaxy in 3/4 of the sky? The first surprise was that galaxies are not uniformly scattered through space. If the universe were just a random, evenly distributed collection of galaxies, you'd expect to see about the same density of galaxies no matter where you looked. But that's not what the data shows. Instead, galaxies cluster together into structures. Some regions of space are absolutely packed with galaxies, like cosmic cities. Other regions are almost completely empty, vast voids that can span hundreds of millions of light years with barely a galaxy in sight. When you map this out in 3D, it looks like the universe is made of a web. Bright filaments of galaxies connecting to form nodes, with enormous empty bubbles between them. It's like the universe itself is structured like a sponge, or like neurons in a brain, or like the world's largest web. The DESI Legacy data revealed this cosmic web structure in incredible detail. Scientists can now trace the exact paths of galaxy filaments, see how they curve and branch and connect to form the large-scale structure of the cosmos. We can see massive galaxy clusters, gravitational systems containing thousands or even millions of galaxies all bound together. These clusters are so massive that they actually warp space-time itself. Light from distant galaxies passes through the gravity field of these massive clusters and gets bent, magnified, and distorted. By studying these gravitational lenses, astronomers can learn about both the distant galaxies and the massive structures bending the light. The dataset revealed the existence of rare objects that were previously hard to find. There are millions of quasars in this catalog, the brilliant cores of distant galaxies powered by supermassive black holes. With millions of quasars identified, scientists can now study their properties statistically. They discovered the most distant quasar ever observed. Light from this quasar has been traveling through space for over 13 billion years. We're seeing it as it was less than a billion years after the Big Bang. Within those 4 billion objects, astronomers also found unusual types of galaxies. There are green pea galaxies, tiny compact galaxies with properties that resemble galaxies from the early universe. These are rare, and the DESI data identified many new examples. There are Lyman break galaxies, young galaxies visible only in ultraviolet light. There are gravitationally lensed galaxies, so distant and faint that they're only visible because the gravity of intervening structures magnifies them. It's like the universe gave us billions of natural magnifying glasses. But perhaps the most profound discovery involves something we can't even see directly: dark matter. Dark matter doesn't emit light, it doesn't reflect light, it doesn't interact with light at all. It's completely invisible. Yet we know it exists because of its gravitational effects. Dark matter makes up about 85% of all matter in the universe, 5 times more than normal matter that makes up stars, planets, and galaxies. By combining the DESI Legacy Imaging data with spectroscopic follow-up observations, scientists can map dark matter indirectly. When light from a distant galaxy passes through regions filled with dark matter, the gravity bends that light slightly. This bending is called gravitational lensing. By measuring how the light from millions of galaxies gets bent, scientists can infer where the dark matter must be concentrated. The result is the first detailed 3D map of dark matter's distribution across our corner of the universe. And this connects to something even bigger. The expansion of the universe isn't constant. The universe isn't just spreading apart. It's spreading apart faster and faster. Something is pushing galaxies away from each other. We call this mysterious force dark energy, but we don't really know what it is. DESI's ultimate goal is to measure how the universe's expansion rate has changed over cosmic time. If dark energy is constant, the acceleration should be steady. But early results from DESI suggest something fascinating. Dark energy might actually be evolving over time. This would overturn assumptions that cosmologists have held for 25 years. By April 2026, DESI had already collected spectroscopic data on 47 million galaxies and quasars, exceeding their original 5-year target of 34 million. Based on measurements from these 47 million objects, scientists found hints that dark energy might not be as simple or constant as we thought. If confirmed with more data, this would suggest that the universe's ultimate fate might be quite different from current predictions. The DESI Legacy dataset is the foundation for all of these discoveries. Without this 5.6 trillion pixel map, showing where nearly every observable galaxy is located, none of these follow-up measurements would be possible. Every single galaxy that DESI measures spectroscopically was first identified in these legacy images. Every rare object discovered was found by searching through this cosmic census. And here's the thing, this dataset is already being used by scientists around the world. Thousands of papers based on the DESI legacy data have been published or are in preparation. Astronomers are using it to study a star formation, galaxy evolution, the large-scale structure of the universe, and the properties of dark matter and dark energy. This single data set is driving an enormous amount of astronomical research. But here's the thing, the DESI legacy dataset doesn't exist in isolation. It's part of a much larger coordinated effort to understand the cosmos. And this bigger picture is actually incredibly important to understand. For decades, Astronomers have been asking what's out there, but more specifically, what's the structure of the universe? How are galaxies arranged? What does the cosmos actually look like when you zoom out far enough to see everything? In the 1990s and early 2000s, the Sloan Digital Sky Survey started this revolution. It was one of the first major projects to systematically map the universe in 3D. Sloan took photographs of the sky, identified millions of galaxies, and measured their distances using a technique called spectroscopy. It revealed for the first time just how structured the universe really is. Those iconic images showing galaxy filaments and cosmic voids, most of those came from Sloan data. But here's the key. Sloan was really just the beginning. It was like the first rough draft of the cosmic map. Over the following decades, newer surveys improved on it. They went deeper. They covered more sky. They measured more objects. The DESI Legacy Imaging Survey is part of this chain of surveys. It's not the final word on cosmic structure. It's probably not even the final word of this generation. The Vera C. Rubin Observatory is coming online soon with the Legacy Survey of Space and Time, which will photograph the entire southern sky repeatedly over 10 years. Euclid, a European Space Agency mission, is currently in space measuring weak gravitational lensing. NASA's Nancy Grace Roman Space Telescope, launching later this decade, will measure even more properties with unprecedented precision. Together, these missions are building an increasingly detailed, increasingly precise 3D map of the universe. Each new survey adds layers of information. We go from just knowing where galaxies are, to knowing their positions and distances, to understanding how much dark matter surrounds them, to measuring how a space itself has been expanding at different cosmic epochs. The DESI legacy data is significant not because it's the final answer, but because it's the foundation that everything else is built on. These images are what DESI's spectroscopic follow-up was designed to work with. When DESI's robotically controlled fibers point at the specific galaxies to measure their properties, the astronomers directing this instrument are using maps derived from the legacy survey images. The spectroscopic measurements feed back into creating an even more detailed, layered understanding of cosmic structure. This is how big science works. Individual projects build on each other. Data from one survey becomes the input for another. Each generation of instruments improves on the previous generation. We're watching a gradual, systematic expansion of human knowledge about the cosmos. And what's remarkable is the democratization aspect. For most of history, only professional astronomers with access to major observatories could participate in cosmic research. But now, because these datasets are public, anyone with internet access can explore the universe. Amateur astronomers can discover interesting objects. Teachers can show students real data from real telescopes. Citizen scientists can participate in actual research. The Legacy Survey Sky Viewer is accessible to everyone. It's free, it's fast, it's interactive. You can zoom from a view showing the entire 75% of the sky covered by the survey, all the way in to individual stars. You can explore the cosmic web, you can find galaxy clusters, you can see the structure that took 263,407 exposures and 8 weeks of supercomputer time to create. This represents a fundamental shift in how science is conducted. Data that was once locked away in university servers is now available to the entire world. This accelerates discovery because thousands of people can simultaneously work with the data, spot patterns, find anomalies, and make new discoveries. So we've covered what the DESI Legacy dataset is, how it was built, and what it shows us about cosmic structure. But the real question is, what does this mean? Why should anyone care? What's the big picture here? Well, here's the thing. This dataset is genuinely transformative for cosmology. It's not hyperbole to say that this represents a watershed moment in human understanding of the cosmos. For thousands of years, we looked at the night sky and basically just guessed about its structure. Now we have an actual detailed map. This map is being used to test fundamental theories about physics. The way galaxies cluster tells us about dark matter. The way that clustering changes with distance tells us about dark energy. The overall structure tells us whether the laws of physics we think are universal actually are. One of the biggest questions cosmology faces right now is, what is dark energy? We know the universe is accelerating in its expansion. Something is pushing galaxies apart faster and faster. We call that something dark energy, but we have no idea what it actually is. Is it a fundamental property of space-time itself, like Einstein predicted with his cosmological constant? Or is it something more exotic? Does its strength change over time? Could it reverse in the future? The DESI Legacy dataset, combined with spectroscopic follow-ups, is helping to narrow down these possibilities. Early results suggest that dark energy might not be quite as constant as we assumed. If confirmed, this would be a major discovery. It would mean that the universe's ultimate fate is not as simple as we thought. Beyond dark energy, this map helps us understand the whole history of cosmic structure formation. By looking at galaxies at different distances, and therefore at different times in cosmic history, we can watch how the universe evolved. Young, distant galaxies look different from nearby, older galaxies. Structures in the early universe are less defined than the structures today. By tracing this evolution, scientists can test whether computer simulations accurately predict how the universe evolved from the smooth early universe to the web-like structure we see today. This also has implications for our understanding of gravity itself. Einstein's general relativity predicts how massive structures should bend spacetime and warp light. By comparing predictions from general relativity with actual observations of gravitational lensing in the dataset, scientists can test whether Einstein's 100-year-old theory holds up at cosmic scales. So far it does, but there's always the possibility that something deeper is going on. Looking toward the future, we're about to enter a phase where this map becomes almost routine. The next generation of surveys, Rubin, Euclid, Roman, will create maps that are orders of magnitude larger and more detailed. Within a decade, we might have 3D positions for tens of billions of galaxies. Instead of a snapshot of the universe, we'll have a time-lapse movie showing how it changes across billions of years. By mid-century, having an up-to-date 3D map of the observable universe might feel as normal to astronomers as weather radar feels to pilots today. What was the density distribution of matter at redshift 2? Just pull up the map. Does this gravitational lens match general relativity predictions? Run it against the 3D model. What was once impossible will become routine. And here's something that's genuinely profound. This map represents a turning point in human history. For almost all of cosmic history, there was nobody observing, nobody studying, nobody trying to map the universe. And then, in this tiny sliver of time, our species figured out how to build telescopes and cameras and computers. powerful enough to actually create a map of everything we can see. We are the generation that went from the Milky Way, is probably the entire universe, to here's a detailed 5.6 trillion pixel map showing 4 billion galaxies across 75% of the sky. That's an absolutely staggering change in knowledge that happened within living memory. And the wild part is, we're not even done. This map is going to get bigger, more detailed, more precise. The future surveys are already being built. The data is being collected. In 10 years, this 5.6 trillion pixel map will look adorably small compared to what we'll have, but that doesn't make this moment any less important. This is the foundation. This is the baseline. This is the map that sets the standard that everything else will build upon. So let's zoom back out and think about what we've covered in the last 25 minutes. We started with the mind-blowing fact that scientists created a photograph containing 5.6 trillion pixels showing 4 billion celestial objects. We talked about the challenge of mapping the universe, a goal that seemed impossible for centuries but became achievable thanks to advances in technology. We dove into the actual details of how this map was built. 263 data, 407 telescope exposures collected over 13 years, processed by one of the world's most powerful supercomputers for 8 consecutive weeks. We talked about the scale and sophistication required to accomplish something this ambitious. We explored what the map revealed: the cosmic web structure, rare objects like the most distant quasars ever observed, indirect maps of invisible dark matter, and hints that dark energy might be evolving over time. We talked about how this single dataset is fueling research by thousands of astronomers worldwide. We put this in context, understanding that this is one piece of a much larger, coordinated effort to map the universe in increasing detail. We're watching a systematic expansion of human knowledge, with each generation of surveys building on previous work. And we're watching the democratization of astronomy as datasets that were once locked away are now freely accessible to anyone with an internet connection. And we look forward to a future where 3D cosmic maps become routine, where the scale and detail expand beyond what we can currently imagine, where understanding the structure and fate of the universe moves from theoretical to observational. Here's the thing that really gets me about this story. We're living in an extraordinary moment. For most of human history, the night sky was a mystery. Even in recent centuries, even as we built better telescopes and developed better understanding, cosmic mapping was always this distant goal. And now it's real. We can actually do it. We have a map of the universe. We can explore it. So here's what I want you to do. First, if you found this exploration of our cosmos fascinating, please subscribe. We dive deep into discoveries like this all the time. Space missions, cosmic mysteries, the latest breakthroughs in astronomy. There's always something new happening in the universe, and I want to keep bringing those stories to you. Second, go explore the Legacy Survey Sky Viewer yourself. Don't just listen to me talk about 4 billion galaxies. Actually see them, zoom through the cosmic web. Search for rare galaxies, see the structure of the universe with your own eyes. The link is in the description. Third, share this with someone in your life who still thinks space is just empty darkness with a few stars sprinkled around. Help them understand that the universe is infinitely more structured, more complex, and more magnificent than most people realize. We are living in the age where we can map the cosmos. That's extraordinary, that's incredible, and that's something worth celebrating. Thanks for watching. The universe awaits.